Okay, so you are constantly, and I mean constantly, surrounded by this invisible digital web. But have you ever actually stopped to wonder how it all works? Hey everyone, and welcome to The Explainer. Today we're diving headfirst into the completely hidden world of computer networking. We're going to break down the whole shebang, from the absolute basics right up to the core advanced concepts, and we'll use a ton of real-world examples to make it super easy to digest. Let's get right into it.
So think about this for a second. Have you ever wondered how a WhatsApp message actually reaches your friend who might be sitting halfway across the globe? Or how exactly the data from a massive YouTube video travels from some remote server right onto your screen in milliseconds? I mean, it kind of feels like wireless magic, right? Well, today we are officially shattering that illusion, because the truth is it's not magic at all. It's a massively complex, physical, and highly structured network.
To really grasp how we got here, let's take a quick look back. Networking basically kicked off in the 1960s with ARPANET, which connected just 4 universities for the U.S. Defense Department. Kind of a humble beginning, right? Then, fast forward to the 1990s, the World Wide Web goes public. The 2010s completely changed the game with the explosion of cloud computing, taking our data off our hard drives and onto remote servers. And now, the 2020s. We are absolutely surrounded by 5G and IoT, the Internet of Things. I mean, literally everything is connected now. Your phone, your watch, your fridge, even the CCTV cameras on your street. The sheer scale of this infrastructure today is just mind-blowing.
All right, to make sense of it all, here is our roadmap for today's explainer. First, local versus global networks. Second, digital addresses explained. Third, traffic cops and devices. Fourth, the rules of communication. And finally, the ultimate network blueprint. Simple enough, right?
Starting us off with Section 1, local versus global networks. Because at the end of the day, all networking is just about connecting devices. But trust me, the scale of that connection changes absolutely everything. The fundamental thing you've got to understand here is the difference between a LAN and a WAN. A LAN, or local area network, is small, tight, and highly secure. Picture your home Wi-Fi, or better yet, a small office setup where maybe 3 computers are hardwired together just to share a single printer and some accounting software like Tally. Because that physical footprint is so incredibly small, an outsider can't just easily hack into it. Now compare that to a WAN, or wide area network. This is the big leagues. It connects multiple cities, countries, and even continents globally. It is literally the largest network out there. I mean, it basically is the internet itself. And you know, what's really fascinating here is that it completely debunks our biggest networking myth. We walk around thinking we are completely wireless. We're not. Honestly, you are only wireless from your phone to your local home Wi-Fi router, or maybe to the cell tower right down your street. From that router onward, your data is traveling through a vast, insanely massive physical web of fiber optic cables. And a ton of those cables are actually running deep underneath the ocean to connect our continents together. It is a wildly massive physical infrastructure. So with all those undersea cables, how does the data actually know exactly where to go? That brings us to Section 2, digital addresses explained. Because just like the post office needs your exact home address to deliver a package, the internet needs a highly specific address to deliver your data. Now, every single device you own has 2 main addresses. First up is the IP address. That stands for Internet Protocol. You can think of this as the logical house address of your device. And the catch here is, it changes. If you take your laptop from your house down to the local coffee shop, your IP address changes because you just moved to a new neighborhood, a new network. But then you have your MAC address. This is your permanent physical fingerprint. It is quite literally burned into your device's hardware, specifically the network interface card right at the factory. And unlike your IP, that MAC address never ever changes. Okay, let's talk numbers for a second. Specifically, the older traditional system for those IP addresses, which is called IPv4. The absolute maximum number of unique addresses this system could possibly generate is roughly 4.2 billion. I want you to let that number sink in for a second. 4.2 billion. Our Earth has over 8 billion people on it. And honestly, most of us have a phone, a laptop, maybe a smart TV, a smartwatch. You see the problem, right? The math just does not add up at all. We literally ran out of these standard IPv4 addresses. There are just way more devices out there than available addresses. So to solve this massive global crisis, engineers ruled out an upgraded system called IPv6.
So where IPv4 is a 32-bit system that uses standard numbers separated by dots, like you've probably seen before, IPv6 is this massive 128-bit system. It uses a long string of alphanumeric characters and colons. And the results? IPv6 gives us so many available addresses that they're virtually limitless. It easily and completely solves our global device shortage. Problem solved.
But wait, here's a fun fact. IPv4 is actually still widely used today. You might be thinking, how is that possible if we ran out? Well, it's all thanks to a brilliant little trick called NAT, or Network Address Translation. See, inside your house, all your devices, the phone, the TV, the laptop, they all have unique, private IP addresses. But the moment they want to talk to the outside internet, your router steps in and translates all those private addresses into just one single public IP address. It's kind of like a huge office building where everyone shares one single public mailing address. It's such a clever trick, and it honestly saved the internet from completely breaking down before IPv6 was fully ready.
And speaking of keeping things organized, that leads us right into a concept called subnetting. Because within a large network, you definitely don't want everyone having access to everything, right? Subnetting is simply the process of dividing one large network into smaller, more manageable, and much more secure pieces. For example, in an office, you'd use subnetting to make sure the HR team, the software developers, and the sales team all have their own completely isolated network spaces. It keeps everything neat, organized, and most importantly, highly secure.
Moving right along to Section 3, Traffic Cops and Devices. Because now that we know exactly how these devices get addressed, how do we actually direct all this massive traffic? Let's take a look at the physical hardware doing the heavy lifting. When we talk about the hardware behind the scenes, there are two major players you need to know: the router and the switch. Think of the router as the smart traffic cop. Its job is to connect completely different networks together, like bridging your home network to the massive global internet. It looks at IP addresses to find the absolute best, most efficient path for your data. A switch, on the other hand, is a bit more like your local postman. It only connects devices within the exact same local network. And instead of IPs, it relies strictly on those permanent physical MAC addresses to pass data from, say, one computer to another in the exact same room. Pretty cool, right? All right, Section 4, Rules of Communication. Because just plugging the hardware in isn't enough. These devices actually need a common language and very specific pathways to understand each other. Okay, let's use an analogy. If an IP address is what gets your data to the right house, a port is the specific door to a room inside that house. And protocols? Well, those are the languages spoken once you actually open that door. So, for example, if you want to browse the web securely, your device is going to use the HTTPS protocol, and it will specifically target port number 443. This highly structured system is absolutely crucial. It ensures your secure web browsing data doesn't accidentally get scrambled up with, say, a file you're downloading via FTP on port 21. It keeps everything in its proper lane. Now, when it comes to how that data actually travels down the wire, there are two main protocols you really need to know: TCP and UDP. TCP is kind of like sending certified mail. It is highly reliable, it meticulously checks for errors, and it totally guarantees that your data arrives in the perfect order. It's exactly what you use for web browsing and sending emails, where accuracy is everything. UDP, on the flip side, is lightning fast but completely unreliable. It literally just throws the data at the receiver with zero guarantees. Now, why on earth would we want that? Well, think about live online gaming or a video call. In those situations, you would much rather drop a split-second frame and keep the action moving rather than sit there waiting for delayed, out-of-order data to catch up. And because that first one, TCP, is so incredibly reliable, it actually requires a very polite little introduction before it sends a single drop of data. We call this the three-way handshake. It goes exactly like this. First, your browser sends a SYN packet, essentially saying, "Hey, I want to connect to you." Second, the server replies with a SYN-ACK, which means acknowledged, "I received your message and I'm totally ready." And finally, your browser sends back an ACK saying, "Got it, let's talk." And honestly, it's only after this strict three-step handshake is completed that your web page actually starts downloading. So we've got the cables, the routers, the addresses, the ports, the handshakes. How does all of this actually fit together into one big picture? Let's look at Section 5, the ultimate network blueprint. Now, if you take a networking class, academics and textbooks absolutely love to teach this massive, complex 7-layer model called the OSI model. But in the real world, the internet practically runs on a much more streamlined 4-layer blueprint called the TCP/IP model. At the very top is the application layer. That's just your web browser interacting directly with you. Right below that is the transport layer, which makes that crucial choice we just talked about, reliable TCP or superfast UDP. Then comes the internet layer, handling all the IP addresses and routing the traffic. And finally, sitting at the bottom is the network access layer, which deals with the physical MAC addresses, the switches, and the literal fiber optic cables. Every single piece of data you send goes down through these layers on your device, travels across the world, and climbs right back up those exact same layers on the receiving server. But hold on a second. Before any of that data actually enters or leaves this beautiful blueprint, it has to pass through a vital security checkpoint, the firewall. You can think of a firewall as a very strict digital security guard standing right at the edge of your network. It inspects every single packet of data trying to get in or out, and it rigorously checks them against a set of strict security rules. If it spots anything even slightly suspicious, boom, it blocks it instantly, keeping malicious cyber attacks from ever infiltrating your local network. Which actually leads us to a pretty fascinating final thought to wrap up today's explainer. We spend our days swiping on glass screens, saving our photos to the cloud, and just generally feeling like we live in this completely wireless era. Yet, as we've explored today, our entire digital existence is actually tethered to physical routers, copper wires, and literally thousands of miles of incredibly fragile cables just resting on the ocean floor. So, if all of this highly physical hardware is what truly keeps our wireless world spinning, just how vulnerable is our modern digital life? I want you to chew on that. Thank you so much for joining me on this explainer today. I really hope this breakdown helped illuminate the hidden web that connects us all. Keep wondering, keep learning, and I'll catch you guys in the next one.